Hey everyone. Today we're going to be learning about momentum and its place mainly in and how we'll treat this in collisions between different objects. And we'll be taking a look at two different types, both elastic and inelastic collisions, and how the momentum of those objects in those collisions behaves. And that's what we're working on in lab, and we're going to kind of get the nitty-gritty behind that starting now. So we talked in class that momentum has to do with an object in motion moving at some particular velocity. And if the object isn't moving, then it wouldn't have any momentum. And this might be something that you've heard of before as far as momentum and had a thought about it, but maybe never knew that the object necessarily had to be in motion, but it turns out it does. An object that's not in motion doesn't have a velocity and therefore wouldn't have any momentum. So the momentum is actually defined as the product of an object's mass and velocity. So if the object's not moving, it doesn't have a velocity, or the velocity is zero, and therefore we'd have no momentum. And we represent momentum by the symbol P. I'm not sure exactly why that is used, but it is defined in the mechanics section on your reference table on the last page. It is a vector quantity, which shouldn't come as a surprise since the velocity is a vector quantity, and therefore momentum gains the direction associated with the vector quantity. So it's going to have both direction and magnitude, or magnitude and direction. And the direction, because it is a vector quantity, the direction of the momentum is going to be the same as the object's velocity. So if the object here, a box moving to the right at a velocity of 6 meters per second, our velocity is to the right, which means our momentum would also be to the right. And if we were to call this a 5 kilogram block, these two multiplied together would give us a momentum value of 30 kilogram times meter per second. And that comes from our equation for momentum, which is the mass times the velocity. And what we want to know is that the P, which stands for momentum, is a product of the mass and velocity, so we have units of a kilogram times a meter per second. M represents our mass, which we know is measured in kilograms, and V measures our velocity, which we measure in meters per second. Now, impulse is how we might change an object's momentum. And in order to change an object that is moving, in order to change its motion or affect its momentum, well, if we're talking about the object, we know that momentum equals mass times velocity. The mass will remain the same. So this, the velocity, must change. And in order to get the velocity to change, we need to impart an impulse to the object. And an impulse is the product of the force applied to an object and the time, how much time we are actually applying the force. So the time during which the force acts. And we'll represent this with a capital J. And since impulse has to do with a force, product of the force applied to an object and the time, force is a vector quantity, so impulse is also a vector quantity. And it's going to have the same direction as the applied force. Again, we can find these equations under the mechanics section in your reference table. So impulse is represented by the force times the time during which that force is applied to the object. Can also be represented as the change in momentum. And change in momentum, to kind of show you here, change in momentum, so the force times the time, or our impulse, has to do with the change in momentum, but the change in momentum comes from, again, our mass won't change, it comes from the change in velocity of the object. So this equation can also be used, and again, another chance for you to see how we can manipulate some equations and turn some things inside out to try and represent different quantities in a different way. So an impulse is going to cause a change in velocity of one or more objects, and therefore we can use that to help determine how long the force was applied, what the force was, or even to figure out what our impulse actually was. So an object in equilibrium, we know that there is no change in its momentum because we're in equilibrium, so therefore your speed is not changing. If it was, we'd have some acceleration and therefore a net force, and then we'd have some change in momentum, but we're in equilibrium here, so no net force. Remember, equilibrium means no net force, no acceleration. Thus, we're going to have no impulse. That should say imparted, not impacted, imparted to it. So what we really want to look for here is the change in velocity. That'll give us an idea of the change in momentum or the impulse. Conservation of momentum we started talking about today in class. For any group of objects not acted upon by any external force, this is what we would call a closed system, meaning nothing gets in, nothing gets out. So they can't be acted upon by any external force outside of that scenario, usually in an ideal situation. Now, from Newton's third law, we say that momentum of each mass has the same magnitude, but it's in opposite directions. So, if we rearrange this here, we can see that the momentum, or change in momentum, of one object has to be equal in magnitude, opposite in direction to the other object. So momentum lost by one equals momentum gained by another. So we're going to conserve our momentum. The momentum that we start with has to equal the momentum that we end with. So another way we can show this, if we add this quantity on the right to the other side, what we end up with, we call this or, m1 times delta v1 plus m2 times delta v2, this has to equal 0. So the total change in momentum must be 0, since we will conserve momentum, and that's what the law tells us. Now, this total momentum that's due to the interactions of these two different objects or two different masses is 0. And that's what we call the law of conservation of momentum. And this is really only going to work for objects in a closed system, which is more theoretical than practical. And the total momentum in this closed system between one or more objects would have to be constant. We'll stop there for today. Quick joke for you. What did the dog say to his owner? My favorite frequency is 50,000 hertz, but you've probably never heard of that. Enjoy the rest of your day.